years ago, I had a paper and the referee came back and said, well, let's just talk about procedure. So, precision is like the estimate of ARE. So, you might have the sigma square of the Thomas square.
So move it down a little.
Now this is just less than 1 than these squares and 1%. And keep that. Square and low cost. Usually you do a square root so you have some. So if you're doing something in this ratio, then comes out to 2, and it's like the Wilcoxon is twice as precise. Actually, you should take the reciprocal. Right?
Wording escapes. And they can have a better expression.
It does mean, if that comes out to 2, that means the confidence intervals for the Wilcoxon are 1/2 as long as those for the square. So you really improve precision. Okay, and you have a more than confidence. Any questions on that? Now remember, for the 2-sample problem, we have an estimate of tau based on 2-sample confidence intervals, which you should use. And we talked about that last time. Okay, so any questions on Wilcoxon? Today then, we want to talk about a couple problems. But today, anyways, let's talk about the 2-sample scale problem. And maybe if we get time, we'll get periods. There are times where you're really interested in the variance. Sometimes you want to even do like a pre-test on variance. Like you want to show that the variance, you want to, null hypotheses would be the variances are the same. And then under that, you can do the 2-sample pre-test with exam witnesses. And Whitney does assume that you have the same variances. Okay. So, but there are other times where the variance is the key thing to limits. And you want to be precise or accurate, and you want to reduce the variance. So now you have two populations. You might do the problem where they could have different location and then a different scale. You do something like this. So this would be population 1. This would be number 2. So when you sample from number 2, that's about the range of the observations you're going to get, right? Whereas if you sample from number 1, you have this long range. So you have much more variation here than you do here. So if you measure variance in terms of the sigmas, then sigma 1 is much greater than sigma 2. And you also have a difference in means. Now, we will talk about the variance-Fisher problem, and that's when you're interested in the means, and you have a setting like this. Although I often think that you're asking the wrong question if you're worried about the means when you have pictures like that. Variance is really change. That's what you should focus. The Japanese, when they built the cars after World War II, Professor Deming, when I learned time statistics, that's what they worried about the most. They didn't want any noise. So if a small location is better in this picture, the Japanese would work on the process to change the mean because they don't have that much noise. Maybe you can shift it down some. You always amaze me when an American statistician really did in our requirements. One more story on that. I had a friend bought a Toyota, and that must have been in the, that's probably still in the 60s. It must have been 2 years. Well, from Pittsburgh area, it's one of the Rust Belt places. You know what? A couple of years later, the Toyotas didn't want to stop. They observed, okay, they were used to that. So the natural null hypothesis here is scales are the same. It's just look at each side, that's what's usually looked at on the scale. It doesn't have to be, you can do one-sided test. Okay. And the thing about scales, right, they're non-negative. So you can take ratios. And then this becomes a parameter of interest, this ratio. So then your goals are to test this hypotheses, and then probably find an estimate and a confidence interval for A. Right? I mean, you could do it on the basis of the confidence interval. If the confidence interval traps 1, then you should reject H0. Okay? Although you get a p-value with the test. remember this from elementary stat or not, but there's the f-test variance. It's just the ratio of the sample variance. But the problem, this test is an extremely poor test, and I recommend that we never use it. And to talk a little bit about that, if you go back to the t-test remains, okay, let's start looking at the t-test remains. Now, this will be exact inference. This gives you exact inference if those populations are normal. What if they're not normal? It'll give you an approximate inference, okay? Because it's asymptotically correct. Central limit theorem says that's asymptotically correct in reach one. I mean, you might not get a T, but you definitely get a Z. So, this is exact. Populations are normal. At least it's asymptotically correct. It's a population are normal. Now you can get, Mann-Whitney might be more powerful here. Generally it will be. But that is at least true. I mean, if someone's doing his inference with a two-sample T, then he's going to lose on power and efficiency, but he's going to probably win on validity. Well, Mann-Whitney's about it too. Well, how about the F-test? This F-test is exact inference. It's a population of normal. It's not. That's implied from the correct. It's a population of not. Okay, this test, you can set up studies where you're sampling not from a normal, but from like a double exponential distribution or something like that. And then you use the self-test and you think you have level 5%, but you might have level 80%. The test is very non-robust. It's not asymptotically correct. There's a constant in here buried inside this simple expression that is zeros, okay, only if you have a normal population, or almost. In general, if it's not normal, the constant's not zero, and you need another standardizing constant, which no one ever uses. So this is a very bad test. So this is a non-recommended test. There are other tests. We're going to talk about the figure thing today. There's also a test for means. I should talk a little bit about the means because that's at least it's asymptotic. This test should not be in the textbooks. It still isn't. You can pick up an elementary textbook and it'll be in there and there won't be any comments on it. So,
I'm sorry, I was going to ask, you think that's why nobody wants their last name associated with that letter?
Actually, it has a, what's the name associated? There is a name. The Spartans. The Spartans. revised program grade has a few measures. It's almost 10 years. But I stuck a good discussion in the book on that test. I wanted to take the test on. Bob says, "Oh, you can't take the test now." I said, "It's lousy." You want to lose. It's like you get the issue. So I just put a big comment. There's a simulation study on it, and I had references in there now. It's Connor over Johnson. It was in Parametric. But the one test that came out fairly good in their study was this figure and clean, and we're going to talk about it today. In fact, they did not do the right figure and clean, because I went back and looked at it a couple of years ago, and I realized I left off a square. So, okay, so how do we do the figure and clean? In the old days, if I was teaching this class about 30 years ago, there are distribution pretests for scale if you assume the locations are the same. In this problem, locations you would never want to assume. I mean, this is often used as a pretest before you test location. You don't want to assume ever that the locations are the same. You're just testing spread. I mean, we did that in the test of location. So I don't want to talk about those tests. And it has a distribution function. I have to use a little notation here. So it's like this. It has some form, that's the way to think of it, and it has a location in it, right? You want to center it maybe. And we have a standard deviation. Then you have these y's. And there's a different location, right? And a different scale. Now you have the same form, we do assume that in this discussion. You could have different forms, all right? There are tests for that. They have different forms, and I'm not sure why you'd be putting this scale. Boy, let's look at the standard deviations and location. Sorry. Okay, so the figure clean. Wigner was, actually he was a young student. Wigner retired from Ohio State a couple of years ago. And Tim Killeen was at the University of Connecticut. And then he became a dean on the other side. I'm sure he's retired. But I don't know anything about that. I don't know about shit. But this procedure, it aligns and then forms a folder. The lines, colons, and then ranks. Okay? So This would be the alignment phase. You just subtract off the medians. Then you fold. Just take that. Now the alignment brings these together. If you had like that one picture we had, we start off like this. But now you align them on the medians, okay? That brings them together. So now you have something like this, right? These would be the stars, right? So now they're aligned, and then you fold them, and when you fold them, that just brings this tail across, right? It's the same distance. But then you're just looking at, I guess, I can just say, you're just looking at that, right? And then you fold the second one, and it's like this. Right? So this would be the line, so that's right. This would be the x. Then the y stars beat the x stars, and you could do what? You could just do a two-sample location. You just combine the data and rank them from low to high. You see the y stars will grab the high ranks. And so your test statistic can be significant. Again, maybe we should have done it on the side, for example, we had it to do. Say the picture is what you think it is. It's not what it is. Here, the next step is combine. I'll just call them folds. Rejection goes here, and reject. Y stars, they lower. Grants. Now, what are possible test statistics for it? It's a very simple problem. You think maybe you could just use the Mann-Whitney-Wilcox, and it doesn't do a very good job. This is a when I first worked on this problem, this is really weird to me. And I'd like the Mann-Whitney-Wilcox wouldn't do a good job. And the thing you're missing here is in the theory, and the theory really takes the logs, okay? And that's the way we'll do estimation. Well, in fact, we could do it now because it doesn't matter. The ranks are invariant to the log. You actually have to think this way. Okay, so I have 9, and I have fold. And you might be able to see that when you look at this. What happens when you fold? It's like you make a speed distribution, right? But logs are a key. We want to take the logs. So really what I should look at is log excellence. Log excellence. Those are natural logs, right? Now you rank the items, then you take the logs, and then you rank the logs, and you get the same answer, right? Because the logs is an increasing function, you won't change the ranks. The ranks are invariant whether you take the logs or not. So for testing, you don't have to take the logs. Okay, but for estimation, you will. Now when you've taken the log, what happens to your data in general? Well, when you take the logs, you can have a very smooth distribution. And if you've done some data analysis, you've probably done this, right? My daughter's working on a problem. I said, well, you have to take the logs. That's really stupid, right? So, when you take the logs, you see the log scale is like this, right? I better draw it, I'll draw it like that. So here you have these big observations, right? You see there's a big gap here. Now take the log scale. Now you're on log scale, so now you're reading the variables over here. There's no gap. Very little. You transformed the data. So it's like you push this long tail in. Okay, so the tail of the distribution, if you did histograms, this would be your histogram before, and afterwards you probably have something like this. In fact, you might get something symmetric. Now, there's a bad case on it too, and that is if you have low values, they explode. So, if you have outliers on the left, you're in bad shape. And I did a problem, an applied problem like this with scientists from Upland. This is our data, it's like this, but then we have this tail on the left. So when we took the log, see, it just on the left, it does just the opposite. So, these are close together, but after you take the logs, then it's not. So you have to be a little bit careful too. You can end up with outliers on the left. Well, anyways, what happens is it's like you compact the data, so it looks, at the beginning you might have a very heavy tail error distribution. At the end you don't. Okay? If you had a heavy tail error distribution, you'd say, oh, I'm going to use the low proxy because it's much less sensitive to outliers. But you don't. You don't. So what you want to do is actually, as you'll see, you explode the tails. This is your test statistic. Okay, you combine the data and rank them, That's the two Conover and Johnson next off. And I think it made a big change. And this would be the inverse of the standard normal distribution. Now you do start at 1/2, so low ones get scored 0. But the score function, we thought this is a function of u, or u is greater than 1/2. Those it has what's what we would call be robust. It's not really robust. Here's the Wilcox. If we did the Wilcox, the score would be this. The Wilcoxons, big outliers get the same way. If there aren't any big outliers, I take the lines. So actually what you do is you explode the outline. It goes up. And here's a scored observation. Okay. Well, the rank of it. Here's a big here's the one on the right. Okay. Here's the Wilcoxon value that goes in its test statistic. And this is the figment means value in its test statistic. So you really explode the right tail. And you don't have anything on the left tail because you fold it. All your actions are from 0 on. Now, first of all, when you look at this formula, what do you think? How in the hell am I ever going to do that? That's a good question. Okay, in R, it's not that bad. Because you have the inverse is just Q norm. It's not really that bad. Minitab, it's a mess. I used to use Minitab a lot in this course before. I set up a Minitab macro for the last 10 years. And then for a while I had it on the web. Fortran. The browser ran on the web. So then what about in passing things? The important thing is the align folding, all right, and then the ranking. And actually, when do you want to do box plots in this situation? Well, you want to do box plots at the beginning, so you see this. But it's better to do the box plots at the end on the line and folded observations, because then you can see the difference in scale. Let's just look at an example. It doesn't matter. And I have those two. The range of the x's are 20 units, and the range of the y's are 60 units. Okay, so looks like there might be a difference in scale. So that's what we're after. And we can do that when we sign the test. If you want. Okay. So then what do we have to do? Well, we just have to align. We need to find a median, which is 16. You might do, you'll, I guess, well, it's 8 minus 16, so we. So there's a line, and then we fold, right? And then we do the same thing to the lines. Then this is another box plot here. We could box plot those, right? And then you can see the difference. So suppose we did do as box plot, these two comparison box plots. We just need what? So it goes from actually 2 to 16. And then Z quartile would be about the second. It would be an extra 2. Not a very good example. Third quartile would be 12. And then these would be 6. And the Y's go from 8 to 6. And then it's 30. So if you box plot that, you can see, the Y's are ahead. So it would go from 2 to 12. And then is 6. So if we would go to 16, so that would be the x's, right? The x stars, and then the y stars would be up on the top. They go from 8. Yeah, the box actually begins at 8. and then to 30. See, it's much more rare. Then on like a quiz question on a figure of eight would be maybe to do something like this. You could at least look at IQ, right? You know, quartile range. I would get. Okay, now I put stuff out on the web. So let's do this example. I have software, and what I want to use in this class is RFit to do the regression and things. And so I built some software that goes along with RFit to compute this. Okay? And I know Minitab doesn't have it. But I thought, you know, for like quizzes or something, I mean, this sort of knowledge is, this is where the, you know, the real information comes. You think you might reject here. The skills are much different. See, the left tail is not that, it's to the right tail. So you're going to end up with like skewness because the left tail can only be here. Right? You can only go down to 0. And if the two y's that form the median, if they were a little more packed around it, this box might be all the way down here. So it's like the right side. See, the log's going to bring that in. But the intuition is in that box. Let's see if this works. I'll pull up the web in a minute, but the web just has these 4 things on it. And the bat means this is where the commands are, so it's like a memory device, which you really need it to get over. And the other 2 are the functions. And of course, for some odd reason, I made that one FKK. I should be able to do this. That is the K sample version. 20 minutes. Now this needs, in fact, I'll show you where this is. It's on crayon, and you can load that library. But then you source that function of k.test.r, and that's what we need to do. And what's the argument to the function is, there's some arguments you can change, but basically it's just fk.test.xy, and this is the original sample. You don't have to do the alignment, of course. Okay. So this one, this one, because this is in. Do it one side, one twenty. But we can bring it up. First of all, let me just get started. Okay, so I'm gonna go in R. I need that library. My library is in. I need the source. This function. So on your machine, you have to know what directory that's in. Sources, okay, so now you can use it. And, we just need to get out some on. You can scan them a few times. You can read things in, but you can scan them too. So you have the data and you check it. And then the test is just so the test statistic is 2.52 and it's that's a two-sided test. I think alternative is less greater, you can do that. Although I think the Y is greater. You can check that. Yeah, we have to do that. That's why we're at. Just the opposite of retail, of course. Okay, any questions on that? So we have a way of looking at it. Certainly in class we can use this function, and some of you might want to download that. Okay, you could test validity. I'm going to just come back 101 on this. Test, and then we'll just to have 100 normals for the X's and, I don't know, 120 normals for the Y's. These would be normal 0, 1, so the scale should be the same. And just do a two-sided test. Thanks. It should be. It is connected. That's good on small size. There might be bugs in it. Let's try. There might be bugs in there, so if you find something that doesn't work, just email it. Okay, so let's just do the confidence interval. So we go back to our initial setup, and of course what you want to get a confidence interval for eta, which is sigma 2 over sigma 1. And then now, I didn't talk about the standardization. You can standardize this, and that's what comes out of that package. And these things aren't nice because this mu fk is this. It's n2 times a bar. And sigma squared fk is this, and this is a. Again, that's not scary. I mean, that's scary for hand calculation, but it's not for the computer. The computer just doesn't have any problem with that. It didn't get hung up on that sum, that's for sure. I know what it got hung up on. So that's your test statistic. If you go back to this scale problem we had, you can write, okay, the x's have this distribution. Then I can rewrite the y's like this. The y's will be y minus 1, 2. And then I want sigma 1 down here. And if you think about this, this says that y minus its mean, I should use theta x. This varies like this, right? It's eta times this. This is a motivator, that's what it should be. Because I really got to translate things back to the apparatus. Eta is sigma 2 over sigma 1, and if the sigmas were the same, then the distribution of this should be the same as the distribution of this, right? But if y is more variable, then sigma 2 is bigger than sigma 1, so the y's are distributed like a big thing times the x, right? Well, in statistics, we often use this notation. We just say distribution of this is equal to the distribution of this. Well then, don't think of it, get rid of that x one. So what I'm saying is that the distribution of y minus theta y is like the distribution of theta times e minus theta, I'm going to get rid of x, where the log of v is the log of x. Again, if eta is 1, then the distribution of y and x would be the same, or this absolute value. Okay. But eta could be large, okay, or small, all right? So then the y stuff is distributed as eta times the x stuff. Now I want to get rid of the x. So I'm just talking about distribution, so I can. I just invent another random variable e, and it has the same distribution as x. So this is my model. See what else in there? I shouldn't say that, but V I can say. That's my model, and then if I just take the logs. Remember, the logs of the product is the sum of the logs. And these are absolute values, so you can take the logs of positive. As a model, it's just a simple 2-sample model, right? And My location parameter is delta, I just call it delta. Delta is the log of eta. And eta is the exponential of delta. So I've turned my problem into a location problem. I can solve that using the Figner-Killeen test, where you'll see the logs are in it now. And then once I estimate delta, then I can estimate eta by just exponentiating. But the exponential is an increasing function, so but I can do the same thing with the confidence interval. So the confidence interval for delta is just e to the lower ci from eta, e to the upper ci. And this is the process I have to look at. That's the process, and then no answer. But this is a two-sample location. That's a lot of stuff. Maybe it doesn't hurt to go over things every once in a while. So you have an idea where things come from. I mean, the program just doesn't come up with these. You have to program that stuff. This one goes. It solves this equation. That's what got hung up. That shouldn't have happened. Okay. So now we have a going back to this. So let's run an example with the other ones. Let's see how well it does the estimate. And we do have the estimates from all of these. And in this case, eta was estimated to be 0.869. It's actually 2 values 1, so it's close, right? And then the confidence interval did track 1. Goes from 0.6 to 1.2. Okay, this is the test of this that we talked about. Let's just run another example. So we would have scale 20, sigma's 20 for the axis. Yeah, that's round, that's just so it looks like we're doing. Oh, there's my axis, right? No, that's not that. Here's, let's think. So they have, population has been 100 and variance 20, and then for Y's. So 53X, still should be 3X. It's 1.3. And the confidence interval was successful. You could check robustness. You could, So the estimate is 1.2. So it's 1.6. So it's like tail sports, so it's kind of. So we have a good robust test of scales. Now, okay, so the last problem I want to talk about, the two sample problem, at least for now, is, well, I have two. We could do the variance Fisher problem, maybe we should. Okay, so there you assume the scales differ, and although I might, and then you still look at location. And the other problem is repair design. I think I'll do repair design. Leave the variance Fisher problem to look at that. So the quiz on Thursday will be what? Well, certainly the two sample Wilcoxon stuff, okay. Moods median could be on it. This stuff, the figure mean will not be on it, that's brand new. So again, it's all the way up to the end of Thursday. Okay. Let's see, is anyone else? Okay. Well, it shouldn't take you long. You should be able to make it.